Hello, I'm Hugh Manfield and welcome to my science channel. Now today we're going to be talking about absolute space, or space-time in general. Coming down from the ancient Greeks and the Renaissance philosophers up through the times of Newton and even to Einstein, there was generally a space denial philosophy where space was assumed to be nothingness and took no part in any material interactions. And as we've developed science further, we're starting to grudgingly give way to some of the concepts that space might actually be a thing, space-time. And the space denial philosophy actually gave rise to the early luminiferous ether theory, which was obviously space-time couldn't propagate electromagnetic waves, and therefore there had to be some medium filling space-time to allow that propagation. Well, since then, we've come to realize that space-time is perfectly capable of propagating electromagnetic waves. In fact, we've given space some properties. The magnetic permeability is a natural constant, and so is the electric permittivity. And those are actually properties of space-time that allow the propagation of electromagnetic waves and give us the velocity of light in a vacuum. So space does have some properties, and there are actually more properties that we can figure out if we're clever. Now we can deduce these properties through examining Newton's laws of motion, which I prefer to call Newton's laws of space. So if Ricky is in a spacecraft out in space with all the windows closed, can't look outside, and is not thrusting with the engines, then she will feel weightless. And this is called an inertial reference system. And from within that spacecraft, there's no experiment she can conduct that will tell her her velocity through space or her velocity relative to any other object. She has to look outside to do this. And this is where we say that an inertial reference frame is not absolute. You can't stick a pinwheel out of the window and measure how fast it turns because of the passage through space. It doesn't work that way. Space is very slippery, and we'll get into more of that later. Now there is something absolute about space, and that is no matter how fast she's moving, no matter which direction she's going, if she turns on the rockets, she will feel gravity. There will be an acceleration, and it's measurable. So acceleration relative to space-time is absolute and measurable, because any other reference frame moving at any other velocity would be able to look and measure that same acceleration that she's experiencing. So if we look at a velocity to time graph, an object moving at a constant velocity will be a straight horizontal line as it moves through time at a constant velocity. Now a constant acceleration will give you a straight rising line as the object increases velocity at a constant rate with time. And if you're in a rocket and it's burning fuel so that your mass is continuously decreasing, it will actually increase the rate of acceleration as the mass decreases. So you'll get this rising curve. And these are measurable things. We can build an accelerometer to measure how fast the speed is changing relative to the starting reference frame. So looking at Newton's exact words, he says for his first law that every body perseveres in a state of rest or uniform motion in a right line unless it is compelled to change that state by forces impressed thereon. Now I've recast that in terms of reference frames for fluid space theory. And Newton's first law, expressed in terms of fluid space theory, is an object will not change its state of motion with respect to any inertial reference frame unless acted on by an external force. And thus, it may be said that objects move through space without resistance. And therefore, conversely, space can move through an object without resistance. Now let's look at Newton's second law. The acceleration of motion is ever proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. And from this we get the force mass acceleration equation. Acceleration equals force over mass, or force equals mass times acceleration. And that's very useful. Probably one of the first uses for it was in computing the trajectories of cannonballs once he had developed his law of gravity, which means, to me, be careful what you discover, because somebody's going to turn it into a weapon. And that's just who we are as human beings. The fluid space theory wording for the second law is: an object will change its state of motion with respect to any inertial reference frame when acted on by an external force. That change will be directly proportional to the magnitude of the force and inversely proportional to the mass of the object, which gives you the same F equal ma equations, but it's in terms of changing its state of motion relative to the starting inertial reference frame, or actually any other inertial reference frame. So when we're out in space, there are two basic and different things going on. We can be obeying Newton's first law, in which case we will feel weightless, it will be floating around. If you release something, it will hover in front of you. Or we can be obeying Newton's second law, where there's a motive force. For instance, standing here, there's a motive force pressing against my feet. I feel gravity. If I release this pointer, it will fall. So I know that I'm in an accelerated reference frame, which is obeying Newton's second law. Inertial reference frames, you float weightless, and objects hover around, and if there's no force acting on them, they stay relatively wherever you left them, unless they had a tiny bit of velocity. Then they'll slowly drift around. When a force is applied within a reference frame, then you feel gravity. And that's Newton's second law at work. And these are two very different things. And that's why Isaac Newton cast them as two separate laws. If he could combine them into one law, he would have. But they are very different things, two separate laws. So in the development of special relativity and general relativity, Einstein did a lot of thinking about reference frames and how they relate to each other. And that's basically what got him developing special relativity. And Einstein says, if relative to a system K, K prime is a uniformly moving coordinate system devoid of rotation. Now that's important. We'll deal with that later. Then the natural phenomena run their course with respect to K prime according to exactly the same general laws as with respect to K. And this is a phrasing of Einstein's first principle of relativity, and you may call it the special first principle of relativity. And it's also referred to as the equivalence principle. Basically, if you're in a box or a spaceship and you're moving through space at a constant rate, and there's another box moving at another rate somewhere else, any experiment conducted in one box will be equivalent to and give exactly the same results as within the other box that's in relative motion. And actually Galileo was the first to propose this, and he used the example of a sailing ship being pulled along on calm waters. And he said if you were down in the hold of that ship and you couldn't see out, you'd have no idea whether you're moving or not. And all the mechanical operations would be the same as if you were outside the ship on solid ground. However, Galileo didn't have the knowledge of electromagnetic theory. Maxwell hadn't come along yet. And then after Maxwell came along, it looked like Galilean's idea of relativity wasn't going to work with electromagnetic theory, because in all reference frames you see the speed of light as c. And Einstein resolved this with special relativity. But Einstein was a space denial supporter, and it was probably the general philosophy that was taught in his years of schooling. Einstein, in some of his writings, if you read his books, he says, "In the first place, we entirely shun the vague word space, of which we must honestly acknowledge we cannot form the slightest conception, and we replace it by motion relative to a practically rigid body of reference." Well, maybe Einstein couldn't imagine something, but he had a contemporary, Herman Minkowski, who definitely could. So Einstein's philosophy was space should be assigned no properties and should not take part in any physical or material interaction. And I believe he was wrong about this. But Herman Minkowski, at the same time, was saying, no, space is something real. In fact, it's probably more real than we imagine it to be. Well, let me quote his exact words. "Hereafter, we would then have in the world no more the space, but an infinite number of spaces, analogously as there is an infinite number of planes in three-dimensional space." Minkowski's not talking about a multiverse. He's talking about multispace. All of these different space-times coexist around us concurrently, simultaneously with each other. Let me give a better example of how that works. Let's say that we're a two-dimensional being living in a two-dimensional plane, and there are two-dimensional objects. So then a theorist within this plane comes up with the idea, well, maybe there's another dimension perpendicular to our two known dimensions of forward, back, left, and right, and there could be multiple spaces. Well, that would be hard for a two-dimensional being to conceive of. How would you even picture that if you were a two-dimensional being? Well, luckily, we're a three-dimensional being. We're actually four-dimensional beings living in three spatial dimensions and one time-velocity dimension. But let's see how it would work when we go from 2 dimensions to 3. So for every point in the two-dimensional system, you can imagine that there's a point out of plane in the third dimension, and it would form a line. All these points at the same point would form a line perpendicular along what we would call the z-axis, or parallel to the z-axis. And if we collect a lot of those points with the same offset from the original plane, that would give us another plane, or multiple planes from 0 to infinity in both directions. And this is what Minkowski was talking about. For 2 dimensions going to 3, there's an infinite number of these planes. Now, might I also add, we could do a rotation of the plane about one of the axes or any line, and there are an infinite number of possible rotations. So going from 2 dimensions to 3 dimensions, there's an infinity of new possibilities for where these two-dimensional creatures might find themselves. So let's carry that forward to 3 dimensions. And we'll reconstruct the same sentence and just change the words. For every point in the 3-dimensional system, there are an infinite number of points in the 4th dimension that exist all at once. So just as when we went from one plane to the other, they could all coexist simultaneously, one plane in the 2-dimensional system didn't preclude another plane from existing. All of these infinite 4-dimensional spaces coexist simultaneously at every point in the 3-dimensional system. And I've made a space-time diagram, which I call my space-time phase diagram, and it would have basically the base plane would be your rest reference frame with space and time, and then as you increase velocity, you rise up through all the layers until when you reach the top, you're at a relative speed of light, and all the axes have swung inward until you have nothing but a straight line. So this represents what Minkowski's talking about that exists all around us. It's a phase diagram of the space we live in. And there could be reference frames moving at any velocity in any direction, coexisting with our rest reference frame, where we tend to think that that's the only reference frame that exists, but it's actually a multispace combined of all possible moving reference frames. And these are translational reference frames or inertial reference frames. So that's what Herman Minkowski meant when he said not the one space, but an infinite number of spaces exist around us. So let's look at the phenomena of acceleration. When something obeys Newton's second law, such as in linear acceleration, curvilinear motion, or standing on a massive body. All three of these represent an accelerated reference frame, because in all three cases you feel gravity. So let's take the example of the rotation or the curvilinear motion. In this case we have a mass moving around a circle at a constant radius, and this is easily explained by Newton's second law. The mass has a velocity and there's a centripetal acceleration perpendicular to that velocity, and if they're in perfect balance, it will cause the mass to move around in a circle. So we can understand this completely in terms of Newton's second law. So circular motion is a type of acceleration. So now what's going on though if we have a spacecraft orbiting a massive body? Here we have Ricky in her spaceship orbiting a massive body. Now her ship is moving in a curve. So we would think, well, this must be an example of Newton's second law at work. Well, actually it's not, because Ricky feels weightless. If she was obeying Newton's second law, she would be thrown to the side of the ship, and she'd have to stand up and be upside down in the picture if there was a force pushing on the ship, causing it to move around in the circle. So what's happening instead? Well, the ship is obeying Newton's first law, so it's traveling in an inertial reference frame. Okay, so why is it moving in a curve instead of a straight line as Newton predicted? Well, that's because of the action of gravity. Now, Einstein took a different point of view of this in general relativity, but in developing special relativity, he realized that he had the example of a window washer falling from the building. As soon as he falls, he's experiencing weightlessness. There's no force acting on him. So gravity is not a force, it's an acceleration. Now, fluid space theory says that we have this inward cascade of inertial reference frames. It's basically the waterfall theory, where space-time is flowing or falling directly inward toward the mass. So what happens is you get a velocity vector field that's always directed in a straight line to the center of the mass. So as a spaceship moves through this field, the velocity vector field changes with time. So what is the change of velocity with time? That's an acceleration. So we can express it either as an acceleration, which causes Ricky to move along the curve, or we can think of it as frame dragging. As a ship moves through space, space is continually falling and accelerating toward the Earth, so the ship follows the natural path, is deflected off its course by the frame dragging of those falling reference frames. And they have exactly the same effect, either the velocity vector field or the acceleration field. They basically do the same job, and they're related to each other mathematically. So when Einstein was developing special relativity, he started with his first principle of relativity, which says that all physical processes behave the same way in all possible reference frames. And you notice he said an exception of rotating systems. He said with no rotation involved. And the reason he did that is because he probably felt that his theory could be criticized if he tried to cover the case of rotation. Because rotation is something a little bit different, and it tended to undermine Einstein's space denial philosophy and his first principle of special relativity. Isaac Newton proposed his bucket thought experiment, where you have a bucket hanging in space in a void, and an observer can walk around it and see that the water is flat, and we don't know what's holding the rope, and we don't know what the observer is walking on. It's a totally isolated system. So then he notices that the rope begins to be twisted through some unknown means, and the bucket begins to rotate. And as time goes by, the water in the bucket begins to rotate as well, and then eventually you have the case where the water is dished, and then if we move into a reference frame that's rotating around at the same rate as the bucket, we would see in one case the water is flat, in another case the water is dished, and if we rotate it even faster, move into that reference frame, the water is dished even more. So how does this work? It looks like physics operating differently for different reference frames. And this was a problem for Einstein and also a problem for Newton. So for Einstein, the rise of centrifugal forces in a rotating body stands in conflict with the space denial philosophy. For example, let's say we have a set of wagon wheel space stations, and they're all rotating at different rates. And then, for the sake of argument, we take about all reference to distant stars or distant matter. We put them in a black void where all they can see is each other, and there's no light source coming from anywhere else. So, living on all these stations, if we take a pole, we might say, oh yes, we have gravity, we're all floating weightless here, we all have gravity on this one, we have gravity. So on all of the space stations, and they're each rotating at a different rate, they all experience gravity, except there's one case where they're not experiencing gravity, they're floating weightless. And this would represent a rotational reference frame that can take priority over all the other rotating reference frames. And this was a problem for Einstein. It seemed to undermine his theory. He needed to have the first principle apply to all reference frames. And he thought that this was a violation of that. And he turned to Mach's principle, which is actually playing mind games with definitions. And Mach would say, no, it is the distant matter that causes the rise of centrifugal forces. So that's pretty much spooky action at a distance. And what's more, he would say, even if the station is rotating, we can declare it to be at rest, and it is simply the rest of the universe that's revolving around that station. Well, that undermines the work of Galileo, who, through great sacrifice, showed that it was not the heavens rotating around the earth, but it was the earth that rotated under the heavens. And it took a long time to get that established as the truth. And Mach would undo that in a word. So when something's spinning and something is not spinning, it's a very basic thing that even a 2-year-old will understand. When the top stops spinning, what does a 2-year-old do? They start it spinning again. It's a gut thing. You can tell when something's spinning, and you can tell when it's not spinning. And that's simply the truth. And what is it spinning relative to? It's spinning relative to space. Because no matter what reference frame you would be in, any object in a rotational rest would be in the same state in any other moving reference frame. Now the top itself will behave the same way in any reference frame. You can take it on a spaceship, move it through space, and it will behave as a top in any of the moving reference frames. So Einstein struggled with this, but he eventually had to come around to grudgingly admitting that space had some properties, and was quoted later in life as saying, as a matter of fact, one should no longer speak of Mach's principle at all. And I think those are good words to live by. Einstein was struggling to understand how rotations could be fit into his theory of special and general relativity. And if you read through some of his early papers, he kind of just hand waves it away and tries to pretend that it's not happening. And this is a classic example of someone who has chosen their theory and want to drive down that road no matter what physical observations say. But if we look at a rotating body and examine closely what's going on, we can understand why there is one rest rotational state and all the other states have centrifugal forces. And we have to understand, back in Einstein's day, they considered material bodies to be solid, one single unit, like a cannonball was one thing. Now, the atomic theory was proposed, and it was coming along. Rutherford had begun scattering experiments and began to find out that even the atoms were mostly empty space. So there was a change happening. But as far as Einstein's thinking went, when he thought of a rotating object, he was thinking of something that's solid, indivisible, and in rotation. He probably thought of it as obeying Newton's first law. For example, if you spin a top in a vacuum with no friction, it will continue to rotate at the same rate indefinitely. That sounds a lot like Newton's first law of translations, only in this case it applies to rotation, and it shows the conservation of angular momentum. And this is sort of an example of how a spinning top obeys Newton's first law. However, it's a rotational sense, not a translational sense. But a spinning top also obeys Newton's second law. So it's kind of a composite object. For example, if we look at all of the different atoms within the rotating body and we choose one of them, it's going to be moving in a circle individually, and we can explain that motion in terms of Newton's second law. So rotation, while it has conservation of angular momentum, it also is a form of accelerated motion. And acceleration relative to space is absolute, and therefore you can measure whether an object is rotating or not. So in an earlier paper, Einstein said that there's no way to tell the difference between gravity in a rotating system and gravity in an accelerating linear system. And that's wrong. There are actually a number of experiments. If you're in a rotating body, you can do experiments and you can determine your rate of rotation and your distance from the center. So it is possible to measure and quantify rotation relative to space. And that's because rotation has this element of acceleration, which is absolute with space and measurable. Now, a rotating body is also a good example of Minkowski's multispace concept. Let's go back to the rotating body. Now, if we think of all the different atoms, zillions and trillions of atoms in this, each one is moving around in a circle, a little bit different velocity, a little bit different radius, and each atom will have its own unique reference frame. Some of them on the rim will have very similar velocities, but at each point along the rim, they'll be moving in a different direction. So if we look at all those potential reference frames all the way around, we can imagine a particle on the rim as it moves around, moving from one inertial reference frame into another, into another, into another. Just as an accelerating rocket, if you drop objects out the back, each one of those enters its own linear translational reference frame, which is unique as a rocket accelerates through a series of inertial reference frames. So we can have all these reference frames going around the outside, and then as we move inward on the radius, the velocity will decrease, and we can have an infinite number of reference frames moving along that axis. So all together, we have this embodiment of Herman Minkowski's multispace concept, where all of these reference frames and potential reference frames make up a rotating system. And it's a system of space-time, which includes all of these frames. So if we look at that on a space-time diagram, a rotating object, the particles within it are moving around and around, and they have different velocities. So a rotating object will not be represented as a point within the space-time phase diagram, such as a constantly moving inertial reference frame would. It would represent a volume within the space-time diagram, from the low velocity at the center to the higher velocities at the rim. And also, these are moving back and forth, or around and around in space, so they would move and trace out. Now, I've drawn a sphere. It probably would be some other type of shape. But essentially, a rotating object would be a volume within the space-time phase diagram. And in fact, if we think of any material body made up of molecules and atoms, and they're all moving around at slightly different temperatures, slightly different speeds, different directions, any physical object that we can think of will actually not occupy a point in the space-time phase diagram, but actually occupy a small volume. So what have we learned about space-time and absolute space? Well, we've learned that space does have properties. It has permeability. It has permittivity. It has absolute acceleration. You can measure acceleration relative to space. And the space-time around us is not just a single space, but an infinite multispace. So I encourage you to think about the space denial philosophy and why it should be abandoned, and we need to move forward into a more of a space acceptance philosophy. For example, now the luminiferous ether was thought to be a medium filling space-time for electromagnetic waves to propagate within. But then we didn't need that ether. Space-time could do that job. Well, there are some other theories out there. What about the Higgs field? Now, what is a Higgs field said to be? Well, it's a field that permeates all of space-time and gives particles the property of mass. Okay, that sounds a lot like an ether theory. Why do we need the Higgs field? Maybe space-time is capable of giving particles the property of mass on its own. And then let's look at quantum field theory. There are various quantum fields that give rise to the various wave functions. And these quantum fields fill all of space-time. Well, do we really need them? That sounds like an ether theory. And maybe we can dispense with the concept of a separate special field filling space-time and just say space-time has the ability to support these various wave functions. In fact, if you think about Minkowski's multispace, as an object's moving through space and all these other multi-space reference frames are there, those reference frames are largely theoretical or unoccupied. And when an object is moving it in a particular reference frame, that reference frame is occupied. Now, if it changes to a different reference frame, that reference frame becomes occupied, and the original reference frame is unoccupied and is therefore more ethereal. And that is beginning to sound a little bit like quantum theory, where the state is potentially available, but it's unoccupied, and then it can become occupied, and when it becomes occupied, it becomes an active state. So if you like this content, feel free to subscribe and click the like button and share it with your friends. And most of the subjects I talk about are in my book, Einstein and Aliens, which is available on Amazon.com. So thinking about space-time can boggle the mind, but sometimes it's good to have our minds boggled. So until next time, I'm Hugh Manfield.